lesson 6.3, which is going to be log rules and solving log equations. So in a lot of these questions, you can actually use them solving methods that we learned about in 6.1 and 6.2. But today I'm going to be focusing specifically on the logarithmic rules and how to apply these. And the calculator I'm going to be using is going to be the Desmos Scientific Calculator. And you can access this by just Googling Desmos Scientific, and this calculator will come up and it will work on a smartphone. So just so you know, that's the calculator I'm going to be using. This calculator will be accessible to you during your test. So I think it'll be useful to practice on anyways. Because everybody will have access to the same one and it'll be more universal than us all using different ones. Now you can do this in another calculator, you will just have to adjust a little bit. So the first logarithmic rule is going to be the change of base rule. And this rule is really useful because it allows us to calculate something where we have a different base other than 10 or e. For log it will be 10, of course the assumed base, and for ln it would be e. Now, that's just a little bit of a correction in your notes. It should be ln there. So the rule is you take the log of x, what you're taking the log of, over log of the base, which is b in this case. The next one is going to be the power rule. So the power rule states that if you have log or ln of something to a power, you can rewrite it as the power times the log or ln of whatever that is. And the next rule is log of a negative. Now we know that you can't take a log of a negative number because you can never put something to an exponential power that will result in a negative. And the next rule is log of 1. Anytime you take log of 1, doesn't matter what the base is, or you take ln of 1, the natural log of 1. Ln is just this log other with a different base, which is e. The answer will be 0. And that's because whenever you put something to the 0 power, the answer will always be 1. And log of base rule. So the log of base rule states that if you take the log of what is already the base, it will come out to be 1. And of course with ln, that will be e. So let's go ahead and evaluate using the change of base formula. So for this one, I'm just going to show you how the change of base works, and I'm also going to show you it quickly using the method that we had learned about on our last set of notes. So this is going to be log base 16 of 64. We set it equal to a variable x. So that's 16 to the x is equal to 64. That could be rewritten as 2 to the 4th power. And this can be written as 2 to the 6th power. So that's 4x is equal to 6, which means x is equal to 3/2. The rule is it's log of 64 over log of 16. That's just using the change of base rule. And that comes out to be 1.5. And you can do that with a few of these, but we're just going to stick to using the calculator for these. So this is log of 32 over log of 8, just using the change of base rule. And that's going to come out to be 1.6 repeating, which is the same thing as 5/3. And this one is log of 54 of log over log of 2, approximately 5.75. And lastly, this one will be log of 1/36 over log of 6, which will come out to be. So on this one, like we could have done it the original way, 6 to the x power is equal to 1 over 36. Well, that's why 6 to the negative 2 power is equal to 1 over 36. So that's why the change of base rule works. So the log rule, this is going to be the change of base rule. So that's log of 1 over log of 5. Well, log of 1 is just 0 divided by log of 5, which is just 0. Log of 1, well, if we look at our rules, we see that log of 1 is just 0. That's the rule number 4. ln of 1 is also 0 according to rule number 4. So D is the rule of base, or the log of base rule, which basically means that if you have the log of something that is already the base, the answer is 1. And the reason this works out is because we have log base 5 of 5. We set it equal to a variable. That'll be 5 to the x is equal to 5, which means x is equal to 1. And this is also the log of base rule. And that's because the implied base of a log that doesn't have a base is 10. So log base 10 of 10 is just 1. And with f, same rule, ln of e is equal to 1 as well, because ln is the same thing as log base e of e, which is 1. So this one here requires the exponent rule. So this is 7 times log base 5 of 5. Now, luckily in part D, we already calculated this. So we found it to be 1. So that's just going to be 7 times 1, which is 7. So basically, this right here is just the rule called the power rule. Okay, the power rule. And the power rule states that if we have a power on the outside, we can simply multiply it by whatever our log is and get rid of the power. So that's why it comes out to be 7. Now we're going to try the power rule again. We have a power, so we can rewrite this as 3 times log of 10. Now log of 10 we just found in this question to be 1. So that's just 3 times 1, which is 3. Once again, the power rule, 2 times ln of e. Well, ln of e is just 1, so that's just 2 times 1, which is 2. And your calculator will also confirm this if you forget. And your notes, of course. You get to use your notes on the test. This is log. This is the change of base rule. Log of 27 over log of 81. So anytime you have the number out here and a number here, you can just do log of this number over log of the base. And this comes out to be 0.75, also known as 3/4. And this is the same situation, but with ln. So it will be ln of 27 over ln of 81. And that's also 0.75, 1/4. So let's talk a little bit about why these came out to be the same. So if you take the log and the log over the log of two numbers, and if you take the ln over the ln of the same two numbers, the ratio is the same and you'll still get the same answer. Because the only difference is they have different bases. And when you have common bases, you set the exponents equal to each other and solve, which will still come out to be the same answer. So this is the change of base rule. Log of 36 over log of 5 is equal to, and like I said, it doesn't matter if it's log or ln, so if you put log in, it will still come out to be the same, 2.23. Now down here, we're going to have to first sometimes apply the power rule. So in this one's simple. It's just change of base, log of 27 over log of 9 plus, now this one here has the 2 on the outside, so that can be rewritten as 2, or the 2 is the exponent, 2 times log base 3 of 27, so 2 times log of 27 over 3 7.5. And you could have done this whole calculation in 3 separate parts as well, and that would still come out to be the same answer. So this is the change of base rule, log of 32 over log of 4 minus log of 2 over log of 4. And that comes out to be 2. And you'll notice these also had a common denominator. So you could have done this as one big fraction. Like that. Now this one's going to require us to use the power rule. So this is 5 times ln of e plus 7 times log of 10 over 3. So ln of e is always 1. That's the log of base rule, okay? So anytime you see ln of e or you see log of 10, those are always 1. So that's 5 times 1 plus 7 times 1 over 3. So that's 12 over 3, which is just 4. Okay, so I didn't record on here, so I'm going to do voiceover. But basically, if you look through the exponent rules, if you don't have a common base, you're going to have to take the log of both sides to solve an exponential equation. You make sure the exponent term is isolated, which it is. So I believe we'll zoom back in here. Yep, here we go. And we're going to take the log of both sides. So log of 6 to the 3x power is equal to log of 8. And then we are going to use the exponent rule here. So we would do 3x times log of 6 is equal to log of 8. And then we have to solve this. So to solve this, we're going to divide both sides by what we multiplied x by. The only variable there is x. Log of 6 and log of 8 are actually numbers that we just don't know yet. So we're going to divide both sides by 3 times log of 6. So we're just dividing both sides by 3 times log of 6 to get x by itself. And when we plug that in, we're going to get approximately 0.39. And here I'm just explaining that if you plug 0.39 back into the original equation, so 3 times 0.39 and put 6 to that power, you should get approximately 8, and that's a good way to check your work to make sure you did it correctly. So on this question, you're going to want to make sure that the exponential term is isolated, which it is, so you're going to take the log of both sides, which is what we're doing. And then when you do that, you see that you have to apply the power rule here. So the power is going to be multiplied by the outside of your log. So you have the product of x plus 4 times log of 3 is equal to log of 1 over 243. So here we're just working on solving for x, so divide by log of 3, which is a number. And then we're just canceling on the left side. And we're just left with x plus 4 is equal to log of 1 over 243 over log of 3. And then we're just going to subtract 4 on both sides. So I just moved the 4 up because it looked like it was on the denominator. It wasn't. And then we're just going to do it as one big calculator operation. So as you can see here, it comes out to be -9 when you do the whole thing in the calculator. And I'm just explaining that you can plug -9 back into the original equation to ensure that you get the same answer, when you do so. And when you do that, you're going to get 3 to the negative 5 power, which is indeed equal to 1 over 243. So now I'm just explaining that 1 over 243 is actually equal to 3 to the negative 5 power, because 3 to the 5th is 243. So similarly to the last one, we're going to take the log of both sides because we have our exponential term isolated. And when we do that, we're going to have to apply the power rule on the left. So it's going to be 3x times log of 15 is equal to log of 285. And then to solve this, we're going to need to divide by both 3 and log of 15 because those are both numbers, the product of two numbers. And that's going to cancel out on my left. And that comes out to be approximately 0.70. So I change it over to approximate equal symbols because it's approximate. So here I'm just explaining that we have to isolate our term with the exponent before we can do anything with this. So I have that negative 2 in the way. So I'm going to have to add that negative 2 to both sides to cancel it out on my left. And that leaves me with 3 to the 2x minus 1 is equal to 5. And now I can take the log of both sides. So I take the log of both sides. And then I can apply the power rule. So the 2x minus 1 is going to come to the outside. That's the power rule. We take the power out, multiply it by our log, and then we're going to have to solve this by dividing both sides by the log of 3. So then we cancel it out on our left, and then we're left with, I try to find a room to write it because there's not a lot of room. We're left with 2x minus 1 is equal to log of 5 over log of 3. So then we're going to add 1 to both sides of that, because remember we're solving for x. And then we're left with 2x is equal to log of 5 over log of 3 plus 1. And then we have to divide the whole thing by 2. Cancel it out, and x is equal to. And here I'm just mentioning that you could have done each one of those calculations separately. You could have done log of 5 divided by log of 3 plus 1 and then divide by 2. You don't have to do it all in one step. But when we do it in one step, we get approximately 1.23. So example 4 says a lumber company has 1,200,000 trees and plans to harvest 7%. And we want to know how many years it will take, or 7% a year. How many years will it take to harvest half of the trees? And this is going to model an exponential function, y equals a times b to the x, where a is the initial amount, b is the factor of change, and in this case, it's decay specifically, because the amount of trees is going down. And now we have to figure out what each of these variables represent, right? So the x is time in our case, okay, in years. And our factor of change, well, we'll do that after. We do y first. So y is going to be the amount that we end up with in the end. And if we're having the trees, the amount of trees, we're going to take 1,200,000 and divide that amount by 2. And when we divide it by 2, we end up with 600,000. So now we're just going to set up our equation in the end, which is going to be 600,000 is equal to your initial amount, which is 1,200,000, times your factor of change, which we have to calculate. So if you remember back to when we first started learning about exponential functions and growth and decay, we have to convert our rate into a decimal, and then if it's decay, we have to do 1 minus that rate. So that's going to come out to be 0.93. Because it's decay, you have to subtract from 1. If it were growth, you'd have to add 1. And that is our b value. And then, of course, we have to put it to t for time. And our goal is to isolate t. So we're going to divide both sides by 1,200,000. And that division comes out to be 0.5 is equal to 0.93 to the t power. And here's where we have to use logs to actually solve this. So in order to solve this, we're going to have to take the log of both sides. So that's going to come out to be log of 0.5 is equal to log of 0.93 to the t power. And now we're going to have to apply our exponent rule here. So the exponent rule says our exponent becomes a product on the outside of our log, which we're going to do. And now we're just solving for t like it's any other variable. So we divide both sides by log of 0.93. And it's going to cancel out on our right, which is going to come out to be approximately 10. So now we're moving on to solving logarithmic equations, and the main thing is you cannot have 0 inside of a log or a negative number, and if you end up getting those are what we call extraneous solutions. So the main idea here is that you need to plug your answer back in the end to check to make sure that you do not receive one of those, because it will be an extraneous solution and you do need to reject it. And then it looks like I added stars for emphasis because you guys know how I feel about extraneous solutions. So on this one, I'm not sure why it just shows the answer, but basically what happens here is you have to put the log's base in, and then it's going to be 10 to the second power is equal to the inside. And then you just have a basic linear equation to solve, 3-step equation, solve for x, and then you would have to plug x back in to make sure you don't have an extraneous solution, which you don't. Now in this one, you have to get the log by itself, so we're going to have to add the 1 to both sides. So we're going to add 1 to both sides. That's going to cancel out, and we're left with log base 2 of 2x minus 6 is equal to 4. And then you just do the same thing we were doing in 6-2. 2 to the 4th power is equal to the inside of the log, which is 2x minus 6. 2 to the 4th power is 16, which is equal to 2x minus 6. Add 6 to both sides, and you end up with 22 is equal to 2x, which means that x is equal to 11. And this will not give you an extraneous solution, because if you plug this back into the original equation, you will not get 0 or a negative number for inside of the log. So on this one, same procedure. You do 9 to the power of 3/2 is equal to 2x. And then you're going to divide both sides by 2 to get x by itself. And when you do that math in the calculator, you're going to get 13.5. And for D, you have a base, you just don't have it written. Remember, ln really means log with a base of e. So you're going to rewrite it with the base. And then once you rewrite it with a base, you're going to do power rule. So it's going to be e to the second power is equal to the inside of your log. And then your goal is to solve for x, so you're going to add 4 to both sides. Now you could put e squared plus 4 into the calculator. You're going to get some number, because remember, e is like 2.71. But don't worry, it's not going to come out to be an extraneous solution. So you can just leave it as e squared plus 4, and that's fine. So before we do anything on this one, we're going to have to apply the power rule. So the power rule for log says that we take our power and we multiply the outside of the log with it. So that's what we're going to do. And now we're going to write in the base of this log. So remember, ln is the same thing as log with a base of e. So we're going to replace it with that. Well, wait, we're going to divide by 3 first. So we're going to divide by 3 first. And now we're going to switch over our log to our ln to log base e, same thing. And then we're going to do e to the power of 3 is equal to 4x. And then divide both sides by 4. And your answer will come out to be x is equal to e to the 3rd over 4, which you can leave as that. That's fine. So this one has a special property of the fact that they both have the same log to the same base. And when this happens, you get really lucky and you can just set the insides equal to each other. So now it's just a regular algebraic linear equation to solve. So we're going to solve it by subtracting 2x on both sides. That's going to leave you with 7x is equal to 21, and we divide both sides by 7, and we get x is equal to 3. So for this one, the same property applies. They both have the same log to the same exponent, so we can just set the insides equal to each other. And when we see this, we see that we're going to have to factor this because it's a quadratic trinomial, so we're going to get it into standard form by subtracting 6x on both sides. We're going to rearrange it, and then we're looking for factors of 8 that add up to -6, which will be -4 and -2. And then we just set both of these binomials equal to 0 and solve. Now, theoretically, you need to plug these back into the original equation to make sure what's inside the log does not come out to be 0 or negative, but neither of these do. So these are actually both true solutions to the equation. So once again, this is the same idea, same log, same base, so we can set the insides of the log equal to each other. And once again, this is going to be a quadratic trinomial. So I'm going to get it into standard form by subtracting 3x on both sides, and I'm going to rewrite it into standard form. Once I do that, I'm going to be looking for factors of -4 that add up to -3, and I'm thinking those are -4 and +1. And then we're going to set each of these factors equal to 0, and we're going to get two results. One of them is going to be negative, one is positive. Now, if I plug the -1 back into my original equation, we have a problem because when we do that, we end up with a negative value inside both of the logs, and they end up to be -3 when we plug them in. So we plug them into either one, and those both come out to be -3, which means that that is rejected, okay? It's an extraneous solution. So we're going to reject -1 as a solution. It's extraneous. Extraneous. All right, so that's the last question. So here I just zoom out so you can see everything. But I know you didn't do this lesson with me in class, so if you have questions, we're going to have a little bit of time to do those before the next lesson, 6-4. So have a great day.